Hello all, we are Group 5 with a presentation on the IntelliPark system, a wireless sensor network for smart parking. The topics we are going to discuss in the presentation are motivation and problem statement, application analysis, network design, hardware and software, implementation, results and evaluation, and finally further improvements. In the Netherlands, there has been a huge increase in the use of bicycles in the past decade. Studies show that in Eindhoven alone, more than 30% of the trips in urban areas are by bicycles. Most users of bikes are students at large universities like TUE. This leads to large parking areas with bikes placed chaotically and a huge loss of time for students to find an empty spot to park. The objective of this project is to develop an intelligent parking monitoring system that can efficiently monitor the actual occupancy of a parking lot and provide the students with real-time data, thus saving them several minutes that they would have earlier spent scouting for a slot. A typical parking slot at TUE has 4 to 8 rows, holding around 40 bikes each, which leads to the requirement of monitoring approximately 300 bike spots. Some of the requirements for the IntelliPark system are: the parking spot status should be updated at least every minute so that when a spot is cleared or occupied, the accurate real-time data is visible to all the users. Low energy consumption. A good trade-off has to be reached between the energy consumption of the nodes and the frequency of the sense and send cycle. Easy scalability. The system should be easily scalable if more bike spots are added or if a bigger parking space is created without needing a huge overhaul in the infrastructure. High security and robustness. The status updates should happen accurately and automatically. No human should be able to manipulate the system to hold a spot for themselves.
Coming to the design of the network, first of all, as this course is about wireless sensor networks and also the infrastructure needed to set up a wireless network is so low, we took the choice of having all the devices in the network to be capable of communicating wirelessly. First, we need the actual sensor that senses if there's a bike present at the parking spot or not, and it should have some way to communicate this data to the users. We are calling these as the nodes. Coming to the choice of the protocol and the protocol for communication and the way for the communication, we have taken some things into consideration. Energy consumption is one of the major constraints that such networks have, as there are going to be hundreds or even thousands of nodes depending on the size of the parking space. So if we can have a network that does not consume a lot of energy, that would save and be efficient. And the other thing is here that there's very less data. All that needs to be communicated to the user is just the state of the parking spot. It's either empty or occupied. And BLE, the Bluetooth Low Energy, seems to be the best combination, the best solution with all the combinations and for our constraints. And even though it has, it's not high speed, but for the data that this network has, it should be more than enough. Next, the BLE is localized. There's no way for a user who's at their home to know whether the parking spot is empty or occupied. So the best thing that this network can have is being connected to the internet. And for that, we need some kind of a translation to happen from the BLE to the internet protocols, the protocol suite. And this is achieved through a gateway. And to connect to the internet, the gateway translates this BLE, the data from the nodes, and sends it through Wi-Fi to the server. And the server could be in the vicinity or it can be on the cloud, and that actually doesn't matter. But for our network, we have a server, and all the gateways and the servers are in the same local area network. And also we have used MQTT from the gateway to the server to send the data. Coming to the scalability of the system, we are using the Bluetooth Low Energy protocol in broadcast mode, which means there's no connection between the nodes and the gateways. This helps with adding or removing nodes to the system and achieving maximum scalability.
Coming to the hardware and software aspects of our project, for the connection with BLE, we have used sensor tag CC2650 from Texas Instruments. For the microcontroller purpose, we have used ESP32 from Espressif Systems. And to act as a server, we have used Raspberry Pi 3B. Now, moving ahead, the implementation under the TI sensor tag. Here, we have used the CC2650 sensor tags from Texas Instruments to simulate the parking of the bike in a spot. We have used 8 of these tags to simulate our design, which means they will be divided into 2 teams of 4 each. To be more specific, we have used the OPT3001 digital ambient light sensor, which was already present in this CC2560 as a way to demonstrate if the bicycle is present there or not. Now, how have we done this? We have done this by setting up the threshold of the measured value of the optical sensor at 120 lux. If the measurement exceeds the value of 120 lux, the parking spot should be considered unoccupied, and if the value is lower than the threshold, then the parking spot should be considered taken. The optical sensor will get new measurements every 5 seconds. The optical sensor will turn itself off after every measurement to save power. Finally, in the total 10-second duration, it can broadcast the same packet every 2 seconds. Now, moving ahead to the ESP part, the ESP has a BLE scan which takes about 5 seconds. In this 5 seconds, we have eliminated the problem of synchronization, as each sensor tag sends one packet every 2 seconds. Thus, the worst case scenario is that we will receive one packet, and in our case, we will be receiving both these packets in the 5 seconds. The ESP then scans these results and checks if the correct packet has been received. If in case something goes wrong and the packet has not been received properly, it will again set up a BLE scan, which again does the synchronization process with the sensor tag. If the correct packet has been received, it will connect to the Wi-Fi and set the MQTT topic. It will send the name as an MQTT message, and the connection will then shift over to the Raspberry Pi. In the ESP32, we have a few synchronization issues which we have taken care as it stays active for the first 5 seconds, and we have used the address and name to correctly broadcast our package onto the Raspberry Pi. The message format of this packet is in the form of the node name followed by the sensor state 0 or 1, signifying if the bike is present or not, followed by the message counter. Now, moving ahead to the Raspberry Pi implementation, here the final phase of the connection is established between the ESP32 gateway and the server hosted on the Raspberry Pi via Wi-Fi using MQTT. ESP32 acts as the MQTT client, whereas the Raspberry Pi acts as the MQTT broker, which subscribes to this data. Node-RED is the tool which has been used to create these MQTT flows and display real-time data in a dashboard. On the Raspberry Pi, a Node-RED MQTT input node is configured to subscribe to a topic, in this case being the parking slot ID like A1. Whenever the slot changes from empty to full or from full to empty, it is published in the ESP32 on topic A1. The Raspberry Pi gets this data and processes it. Now, how this processing is done? It is done in the form of change of the color icons, such that when the color is red, it indicates that the parking slot is occupied, and when it is green, it states that the parking slot is free.
Here we show a simple demo of our system. The sensor nodes are placed on blue papers. Each sensor node would be placed in a parking spot. As the light sensor tells whether the bike is parked or not, we simply flip the sensor face up or face down to represent these states. Each paper represents a parking lot. Each parking lot has a gateway that gathers information from sensor nodes via Bluetooth from its assigned area. Finally, the server will collect information from the two gateways via Wi-Fi. Two nodes are flipped upside down, A3 and B4. Initially, all nodes are faced up, meaning that all parking spots are available, thus there are lights. There is a delay between the light sensor reading and the data being presented on the screen due to the network constraints. About 25 seconds later, both sensors are correctly identified as occupied. Then A2 and B2 are marked as occupied. After 25 seconds, A2 and B2 are both marked as occupied, A3 has arrived marked as available, and B4 just changed its states to the available again. In this demo, we keep on changing the sensor node's states and the values are updated on the server. Some devices take more time to update their values on the server, like B3, but they will eventually be updated. Ideally, that would be great if the system could be updated in real time. However, taking into account the energy constraints imposed by the system, those delays are inevitable, and they bring no harm as long as they follow the latency requirements.
As we mentioned before, the optical sensor performs a light measurement every 5 seconds, and every 10 seconds we construct a new message that is broadcasted and received by the corresponding ESP. Then this message is broadcasted every 2 seconds until a new packet is constructed. So even if the state of the sensor has changed, the maximum time between a sensor state change and the broadcasting of that change is 10 seconds. Between these 10 seconds, the sensor will keep broadcasting its old value. The reason for scanning 2 times in the 10-second window, even though the first value will be discarded if there is a state change, is to make sure that the sensor tag will have updated data to transmit every 10 seconds, in case the optical sensor did not take any measurements in the first half of the 10-second window, achieving high quality of service. This means that the best waiting time between a change in the sensor and its advertisement is 5 seconds, and the worst, 10. However, if for some reason the ESP does not pick up the first advertisement of the packet, it will receive the same message after 2 seconds. We left the application running for 2 hours, and at the end, all packets that were sent by the sensor tag were received by the ESP32, meaning that we achieved the highest packet delivery ratio. However, if the system is scaled up to include hundreds of nodes, we can expect that this PDR will decrease. The worst latency that can occur in this application is 25 seconds, 10 seconds for the sensor tag and 15 seconds for the ESP32, as it is mentioned in the implementation. On the other hand, the best latency that this application can achieve is 10 to 12 seconds. That is 5 seconds for the new measurement to be transmitted by the sensor tag and 5 to 7 seconds to be received and transmitted by the ESP. This can be considered acceptable for this kind of applications where the data are not critical for human survival, like monitoring the health vitals of people working in mines, where even 20 seconds of exposure to dangerous air, like carbon dioxide, can play an important role. Finally, as the data from the sensor nodes is broadcasted, even if the respective gateway misses the data, there is a chance for another gateway to listen to the packet and send it to the server. Also, the ESP32 sends one message for each packet from the nodes, and this redundancy helps with the system being up to date. For future improvements, there are some functionalities that could be implemented. We list some of these possible improvements. The user, for example, can install an application on their smartphone that can provide an interface for all system functionalities. In the app, the user can find the parked bicycle. As soon as the user parks their bike in a spot, they will be notified via the app about the bike GPS coordinates and the parking slot ID. This way, the user can find where the bike was parked faster. The app can also provide a spot reservation system, so the user can be sure that there will be a spot available as soon as they reach the university. This reservation will be available for a given time, for example, 30 minutes. If the user does not show up in time, the spot will become available once again. Notice that for this implementation to work, it's necessary to add an extra piece of hardware to lock the spot so no one can park but the user. Finally, the system could have a power preservation scheme by implementing two working modes. During the day, parking spaces are filled and emptied constantly, so we need a fully working system. On the other hand, during the night, finding a parking spot is not a problem, so we can expect our sensor network to suspend its function to preserve power. Thank you for your attention.